Hello, people watching this video. We are jumping right into section 5.1. Exciting things about chapter 5. I've already told them that we have no more online assignments. Yay! That just means there's a lot of work for some of these problems. Not necessarily in chapter 5. Chapter 6, we start to get kind of a little bit heavier of a load into, like, you have to write your workout stuff. Chapter 8, we do like something called hypothesis testing. That's like huge, full-blown. There's like 13 steps per problem. Okay, lots of stuff going on, all right? But we'll get to there eventually. Chapter 5, all in paper, pencil, homework assignments. All right, so we've got some, just like each one of these chapters, they front load it with some vocabulary stuff. And we have random variables, we have probability distributions, we have discrete random variables and continuous random variables. Okay? So let's kind of talk about, I'm going to skip down to the bottom too. Let's talk about the difference between discrete and continuous. Do you guys remember when we talked about discrete versus continuous? What's the difference between discrete versus continuous? No? Discrete. I'll give you a little hint. Discrete is countable. Countable. Discrete, countable. Okay? So a discrete random variable would be something that I'm like trying to find the probability of that is countable. Like, how about we say the number of fives when roll dice 20 times? Can you count that? Can you discretely count how many fives you get?
Yep.
Yes, correct, you can. Okay? A continuous random variable would be on a continuous scale, and continuous is like the decimal numbers that go on forever, right? So what's a continuous variable that we've talked about before?
Counting stars.
No, that's discrete, because there is a finite countable number of stars. Heaven forbid we actually have to solve that, because it's a lot of them, right?
I believe you.
Right now there is a finite number of stars.
But
I wouldn't be able to count them because there's too many of them. But continuous means that it has a decimal that goes on forever, right? Like weight. Like your scale will say that you are 150.25 pounds, right? But you're probably not 150.25 pounds exactly. You're probably like 0.253476132 pounds, whatever, it goes on forever. What? Kind of like the number pi, but like talking about like things that we're measuring. Like pi only has one measurement, but things that we're measuring, but it's kind of along those same lines. So continuous means like a decimal. Decimal goes on forever. So a continuous random variable would be like weight or like distance, because it could be 1 foot, or it can be 1.1 foot, or 1.11 foot, or whatever. Weight, distance, temperature is another continuous random variable. Okay. A probability distribution, we're working our way back up. Probability distribution is the number of times each one of these is occurring. Okay. So like, the probability of each variable occurring. Okay, so a probability distribution. Here's an example of a probability distribution. I'll do a really easy one. Okay, probability distribution. It will be set up to look exactly like this. You'll have an x, and then you'll have a p of x. X is your variable. P of x is the probability that happens. Okay. I'll zoom out a little bit, okay? Probability of each variable occurring, x and p of x, okay? So let's say my x's are 1, 2, 3, 4, 5, 6. I'm rolling dice, right? What would p of x be? 1 out of 6, 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 right? Because each one of those has an equal chance of happening, assuming we're using a fair dice, right? This is what a probability distribution is, this table, right? Probability distribution is a table. It's showing all of that good stuff, okay? And then a random variable is just something that we're looking at probability for. What should we put for random variable? It's like the weight or the whatever you're rolling. They say is a variable typically represented by x that has a single numeric value determined by chance for each outcome. Okay, so a single value, let's just say that. A random variable is a single value let's see, a single value for which, let's just say for which probability can be assigned. How about that? Does that make sense? Okay, like a single value would be like rolling a 2. I can find the probability of rolling a 2, right? A single value. Okay. Does that make sense? And then within those, so random variable, we have a discrete random variable, continuous random variable. Those are just more further describing what types of variable those are. Okay? Good? Make sense?
Can you leave that there?
Yes, I can. We have a checklist of things that are required in order to make a probability distribution. Like you can't just do a probability distribution with anything, right? Or some qualities about probability distribution. So this is a probability distribution. What has to take place? Look at the probabilities. What's one thing you notice? They don't all have to be the same. They are in this case, right? They don't all have to be the same probability, but they have to do what? Add up to be 1, right? They add up to be 1 or 100%. That's one of the requirements of a probability distribution, okay? All right. The sum of the probabilities is 1. That's what number 2 says, right? The sum of all the p's is 1, okay? Now, they are cautioning you. I'm going to talk about 2 a little bit further. It says the sum of all probabilities must be 1, but sums such as this or this could happen, right? 0.999 or 1.001 can happen. Why? Like if we're adding those all up together, you might get 0.999 when you add them up together, or you might get 1.001 when you add them up together. But why does that happen? Because of rounding errors, okay? So the probabilities have to add up to be 1, but sometimes it's awfully close just because you've rounded, okay? All right, number 1, there is a numerical random variable, and we're not talking about categories, right? We're not talking about, you know, like red, blue, green, whatever. We're talking about numerical values that we can set probabilities to, okay? And then the probability for each one has to be between 0 and 1, right? You can't have probabilities that are negative or over 100%, right? Those are just kind of common things that have to take place, okay? Good? All right. Coin toss. Let's consider tossing 2 coins with the following random variable. Okay, let's talk about this. Here we go. I'm going to write a table off over here. And we're going to talk about combinations that we could have, combos that we can have when we're tossing 2 coins. So this is like the sample space. What could we have when we are tossing 2 coins? What could happen? I could have heads, right? That combination. I could have heads, tails, heads, or tails, right? Okay. Okay, we're going to have like kind of 3 columns here, okay? Now, what we have to do when we're doing a probability distribution is we can't look at 2 things at once. We can only look at 1 thing, okay? So right here, rather than talking about the combos that we have, we're only looking at the number of heads, right? We have to focus on one of them. We can't look at both of them at the same time. We're focusing on just the number of heads that we get, okay? So that's going to be the x. X is the number of heads that we get, okay? And it doesn't have to be heads, it could be tails, but you have to choose one of them. We can't look at both at the same time. So if I'm doing those combos, the number of heads for the first combo, that x value would be 2. The x value for the second one would be 1. The x value for the third one would be 1 again, right? That has 1 head, and then the bottom one has 0, right? Okay, now let's talk about p of x. What is the probability of getting 2 heads in a row?
0.25.
1 out of 4, right? Okay, 0.25. What's the chances of getting a heads-tail combo? 1/4. What's the chances of getting a tails-heads combo? 1/4. What's the chances of getting a tails-tails combo? 1/4 also, okay? But hold on. look at the way that they set their table up. They did their X's over here and they did their P of X's over here. They only have 3 of them instead of 4 categories. And they have 0.25, 0.5, and 0.25. What the heck did they do? No, they did count as 0. Look at their X's. They have 0, 1, 2. Right, they just lumped these two together, right? So in that case, they're looking at heads, tails versus tails, heads, meaning it doesn't matter what order they go in, right? They're just looking at one head in general, doesn't matter the order, so it could be heads, tails versus tails, heads. So they combined those into one to make this one category, and that's why it's worth 50%, right? So you have a higher chance of getting 1 head than you do of getting 2 or 0, right? Because it could be a heads, tails, or tails, heads, right? You have a higher chance, okay? So if we graph that, this is my graph of that probability distribution, okay? You can kind of see that bell-shaped curve a little bit, even though we only have like 3 bars. You have a higher chance here in the middle of getting exactly 1 than you do of 0 or 2, okay? Let's take a look at the way that this graph is set up. They have the probability always on the side and they list it as a decimal. So 0 being down here, like 100% being up at the top, okay? They just went to 50% because that's the highest they get. And then these are the categories that we have on the bottom, 0, 1, and 2. Make sense? Yeah? Okay? So there's kind of how that works. That's a probability, that's a histogram of the probability distribution. Okay? Are we following along? Is this okay? All right, not too bad so far. All right, so let's talk about and let's make a probability distribution for the birth of 3 babies. Okay, so we're looking at 3 babies, and let's list our combos here. Okay, let's list the combinations for 3 babies. Okay, let's decide how many combos are we going to have. I have 3 babies, 1, 2, 3. Okay, the first one could be a boy or girl, there's 2, right? The second one could be a boy or girl, that's 2. The third one could be a boy or girl, that's 2. So I have 8 total combinations, right? Ellie said that to begin with. 8 total combinations. So this list is going to be 8 long, right? Let's start listing out some combos. What could I have? Boy, boy, boy. Okay, I'm going to go to the very bottom and I'm going to go girl, girl, girl. There are exactly 4 combinations that start with boy and 4 combinations that start with girl. Boy, boy, girl. Boy, girl, boy. Boy, girl, girl. Okay? I can't like even say these words because there's like too much. Okay, let's start with the girls. We're missing 3, right? Girl, 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 boy. Girl, boy, girl, and girl, boy, boy. Those are my combos. I don't know. You can put them in any order. I don't care. No, whatever. I just tried to make them mirrored, right? Like, do they mirror, right? Like, these 2 are close together, so boy, girl, girl is the same thing as girl, boy, boy, right? Boy, girl, boy is the same thing as girl, boy, girl. I just tried to, like, mirror them, right? I don't know. I don't know what the right method is, just as long as you get all 8 of them, whatever. So anyway, there's that. Okay, but they will pick on one versus the other, okay? They'll just lump them into categories and say, we don't care about order. So we're going to say order doesn't matter. Okay? We just care about boys versus girls, okay? I could get 3 boys, 0 girls, okay? Now, let's do P of X. Let's talk about, like, the chance of that happening, okay? What's the chances that I'm going to get 3 boys, 0 girls? 1 out of 8, right? This is the only combination that has 3 boys, 0 girls, right? Okay? Now, what's another combination I could get? 2 boys, 1 girl, okay? Now, this one's just a little bit trickier because 2 boys, 1 girl. I have 2 boys, 1 girl.
The next one is also.
I have 2 boys, 1 girl.
And then you have
one at the bottom, 2 boys, 1 girl, right? So what's the probability that that's going to happen?
3 out of 3.
3 out of 8. So that has a higher chance of that occurring, right? Okay? Okay, then I could have, I could do 1 boy, 2 girls. Or the last option is 0 boys, 3 girls. Okay, so let's figure out those combinations. All right. 1 and 2, 1 boy, 2 girls, 1 boy, 2 girls, 1 boy, 2 girls. I'm trying to do them in different colors here. 1 boy, 2 girls, 1 boy, 2 girls, 1 boy, 2 girls. That happens.
Also
3 out of 8 also, okay? And then the chances of me getting 3 girls and 0 boys is just this combination. That is 1 out of 8 as well. Does that make sense? Okay, so this is my probability distribution. Now, usually in the probability distribution, we'll pick on one or the other and not both. We won't put both combinations there. So we're going to do boys or girls? Girls. Okay, so we're going to say X and P of X. And we'll just say that these are the number girls. And P of X is that. So they'll only give you like half of the table, right? So X would be 0 girl, 1 girl, 2 girls, 3 girls. And then the probabilities will be next to those. So 1/8, do you know what 1/8 is as a decimal? 0.125, yeah. 3/8 is a decimal. Multiply it by 3. 0.375. 2 also occurs at 3/8. That's 0.375 again. And this one occurs 1/8. So this is 0.125. Okay. If I make that into a table, or a chart, a histogram. Okay, we got lots of stuff going on here. Sorry guys, you got a lot of notes. These are my probabilities. These are my X equals the number girls. Okay, so I'm going to do 0 girls, 1 girl, 2 girls, 3 girls. Okay, I'm going to put 0.125. This would be 0.25 and 0.375. And I've got something that looks like this, something that looks like this, and like this. And that's my histogram for that probability distribution. Okay, so they'll always set it up as one versus the other. So we chose girls just like they chose heads above, right? And that's kind of how they'll separate it out, okay? Notice that these still kind of resemble that bell-shapey thing, right? Do you guys see the bell-shaped curve-ish a little bit? Do you see it? You see it? Kinda, ish, a little bit. Okay. Well, we're graduating into that, is to that bell-shapey curve thing. Yeah. Good. I will zoom in or out. In on these guys. That one. Okay. Okay.
We should stop.
You think we should stop?
Yeah.
Let's do an easy example. Let's do the back. Just one more. I'll show you. It's easy. It's easy, Caleb. And we'll just knock it out and it'll be done. Okay, ready? Go to example 2. Go to example 2 on the back page. We'll skip the top part, but go to example 2. Check it out. Does this table describe a probability distribution? So they're talking about reasons. They're talking about stupid things that people do when they're getting job interviewed. Okay? Inappropriate attire. 50% of the time, people were not hired because they were not wearing the right thing. Being late. Are you kidding me? 44% of the time, they were not hired because they were late to the interview. Don't do that. That's stupid. Why would you do that? Lack of eye contact. That is a legit thing, right? Like people are really struggle with that sometimes. You want to make sure you have eye contact while you're doing this. And then checking phone or texting while you're taking an interview. Is that even a thing? Do people actually even do that when they're interviewing for a job? Oh, looking at their watch. That, I could see that, right? So you're going to get dinged if you look at your watch. Like you have better places to be than for interviewing for a job, right? Yeah, that's how they take it, okay? These things. Is this a probability distribution? Does this resemble a probability distribution?
No.
How's come?
Over 100.
Look at this, 157%. No. What's probably happening is these people weren't hired because they were doing 2 of these things at one time, right? Like they're counting 2 categories in one. So maybe somebody was late and they weren't wearing the appropriate thing, right? So they but they're only, so they're not accommodating for the double reasons, right? So no, this is not a probability distribution. No. Over 100% or 1 as a decimal. Okay, there you go. We'll stop.
Can you go back to the
Yep. No, it's over 100% or 1. Back to the graph. There you are. Okay? All right, I'm going to stop the video and then I'll get back on, Erica. Okay?
Yes,